Okay, welcome everyone. I hope you can hear me, Joel. Joel says it's okay. We are back. It seems I managed to lose half the class. That's okay, I don't mind. For those of you who are in F5, there's actually a lot of high quality places available here. It's fun. Come on here. Then we don't have to broadcast across. For those of you who will be watching this in July, you should have been here right now. It's much more entertaining. Okay. So yesterday, it was light, it was fun and things like that. But today it's going to get a little bit boring. We start with binary numbers. So binary numbers are numbers where we have only 2 digits, 1 and 0. Now, we want to talk about how we can express anything meaningful other than 1 and 0. And after a while, we'll come and explain to you how great hexadecimal numbers are. And then we will, the counting part is really easy, right? I mean, humanity started with this thing. You had a number of sheep. You wanted to know how many sheep you had. You started counting them. Everything was great. At some point, humanity invented 0. When you said, I don't have any money, 0 money, okay. And the concept of negative numbers was a little bit more difficult, right? So we will also see the type of difficulty we have when we want to deal with negative numbers, because, trying to count them, after all, is a permutation, right? If you have 4 fingers, how many different numbers can you express with 4 fingers? Everybody's looking. Okay, let's make it 5. Anybody, any idea? If you had a secret information, you're playing football, how many different codes can you send? Yeah? 6. Who says more? Whoa. Who says 245? Really? Okay. At the end of the lecture, probably we'll have a better understanding of this thing. And then once we have, these people love to compute. Yeah, okay, calm down. Once we have negative numbers, we will be able to also do addition and subtraction, because if you have negative numbers, you can add a positive and a negative number is the subtraction. Okay. I mean, people are still on that. Okay, let's take it to the break. Okay. Man, I made a mistake. No, I cannot. Hello. Okay. So number systems, most of us know the decimal number system. So when they say 5,374, you can easily understand what this is about, and you can look at it. And the binary numbers are actually totally the same. There's nothing very interesting about it. So you have when you have a decimal number, so this is the first column, so it means 4 times 10 to the 0, 7 times 10 to the 2, 3 times 10 to the 2, 5 times 10 to the 3, whatever. And this one is the 1's column, the 2's column, the 4's column, the 8's column, technically speaking. And if you were to expand this, you say, okay, this number is, we have 5 times 1,000, 3 times 100, 7 times 10, 4 times 1, and then you add them together. Why should binary numbers be any different? Well, they are not. So it's just that it's a little bit weird, like saying, what is this actually? Well, it's 2 to the 3, and what is 2 to the 3? 8-ish? Something else, something else, something else. And if you add them up, you will realize that this weird sequence means 13. Now, if we want to continue this lecture, we have to sort of kind of know what the powers of 2 are. Now, there's ChatGPT, of course, but it's not so bad to sort of kind of keep this in mind, right? So these are the powers of 2. Do you know any one of them? Like, who knows 2 to the 11? Great. 2048. So these are if you are anyway associated with hardware design, those are round numbers for you. And don't get overexcited, okay? It happened to us. We are a couple of friends. We went to a bar. Bill comes back, and it was 128 francs. And we said, wow, 128, that's a round number. And Peters was saying, like, it's 128. We say, yeah, to the 7, 128. She walked away. So don't do that. So it is actually handy to, I mean, the first 8 probably, right? I mean, we are not saying you should memorize it, but it comes in very handy. So the first 15, 16 of them, you will encounter these numbers quite a lot. So it helps to know them. But it's also not so difficult to calculate them. You know, if 2 to the 6 is 64, 2 to the 7 is 2 times 2 to the 6. So 64 times 2 makes 128. That's the way it's calculated anyway. So how do we convert it? Now, I'll use this one. What is it? 10011. Okay, we can never do this while you're teaching. Okay, can you tell me some numbers? 1, 0. Yeah, say. Well, 1, 0, 0, 1. Oh my God. Okay, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. Now, since you memorize all these numbers, right? So this is 1, this is 2, this would have been 4, this is 8, this would have been 16, and this is 32. So we add them together. 32, 40, 42 would have been perfect. Okay, next one I'll do that. So not exactly the same number, but the same principle. 2 to the 4 times 0 times 2 to the 3, 0 times 2 to the 2, etc., etc. When we write those down, we get the equivalent. So it's 16 plus 0 plus 0 plus 2 plus 1. In this case, it's 19. In case you're wondering, yes, we will ask something like that in the exam. Okay? You shouldn't be surprised. Nobody should be. And yeah. In case you're wondering, we are not allowing calculators into the exam. Yeah, not fair. I know, horrible. Now, when you want to convert from decimal to binary, the story is a little bit annoying. Because essentially, I mean, you will do the same thing when you do a decimal conversion. I mean, when you would convert something to decimal the same way. So now you have 47. So is there a power of 2 in this number? That's your question. So you're picking a power of 2 that you think is close to this. So you have this entire list in your head, right? 2 to the 6, 2 to the 5, 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1, blah, blah. 2 to the 6, who remembers? 64. So is this number larger than 64? Larger than 64? No. Okay. So what's next? Is it larger than 32? Larger than 32? Yes. So let's subtract 32 from it. What's left? 15. This one, 16. Is it larger than 16? No. Okay, next one. Is it larger than 8? Yes, let's subtract it, etc., etc. I'm not going through the entire calculation because I have a nice slide which does exactly the same thing. So is 64 larger or equal to 47? No. 16, 15, da, 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 da. We make our choices. No, yes, no, yes, yes, yes. And then when you read it down, 0, 1, 0, 1, 1, 1, 1 seems to be 47 in binary. So 0, 1, 0, 1, 1, 1, 1 makes it. Amazed? Okay, will you manage it in the exam? I hope so. Now, yes? It's a very good question. Excellent question. We'll come back to that. Very, very nice question. See how I'm deflecting? Okay. So question was, sorry for the recording, why do we start with a 0? You know, we could have If we were like smarter, the first question we would have asked was, is it larger than 32? It would have been 1. And we would have also said 1, 0, 1, 1, 1, 1, which is also true. And I could have also said 0, 0, 1, 0, 1, 1, and it's also the same number. We will come back to that, but it's a very good question. Now, binary values in range. Now, you've seen that if I have an n-digit decimal number, if I have 5 decimal digits, how many values can I represent, and what's the range? Now, we know that decimal system, right? So if you have 5 numbers, you can go all the way to the 10 to the n. And, you know, these are all the numbers from 0 to 99,999. So 10 to the 5 minus 1. The similar thing, 3 digits, sorry. So 3 digit, 10 to the 3 makes 1,000, so the range is from 0 to 999, inclusive. Now, when you do a binary number, it's exactly the same. So I'm coming back to the question I asked at the beginning. If I have 5 fingers, how many different numbers can I represent? 32, and the range would be from 0 to 31. Let's see if this is correct. It is correct, but we have a different example here, 3-digit binary numbers, 2 to the 3, 8 possible values. So it's 0 to 7, anything that starts 0, 0 to 1, 1, 1. Great, excited? Sorry, I forgot to tell you. These first few lectures will be a bit boring, okay? It will get better. And you know, I'm not doing this because I want to ask evil questions in the exam. We need to build on these. And yes, I'm sorry, it looks very mundane and things, but you know, allow us to build up, okay? No trust at all. So then we started with these hexadecimal numbers, which seem to be a very weird thing. So these are the decimal numbers. You go 0, 9, 10, 11, 12, 13, 15. You have the binary versions 0, 0, 0, 0, 1, 1, 1, 0, something, something. And then the hexadecimal numbers all the way to here are the same as decimals. And then we go A, B, C, D, E, F. Yeah, why not? I mean, you could also come up with different things. But these are actually quite useful for us. You know, the main reason is because for every 4 binary digits, I have just one interpretation of a hexadecimal digit. So instead of writing a very, very long sequence of 1s and 0s, something like, okay, anybody helping me out here? Yeah, say something. Let's say 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, 1. This is the salary you're getting, okay? Now, is this a good number? Is this a bad number? So, and you know, somebody is calling you, or this is your phone number, and saying, what was it again? And you're saying, 1011011 1011 0111 110. Okay, but you notice that if you divide this up in chunks of 4, you can easily interpret this, and you know, with a little bit of getting used to. So this 8 plus 4, 12, 13. 13 is 11 is A, B, C. Okay, this one is 7. 8, 2, 1. Yeah, sorry. B. Of course it was the, I was just testing it. Great. You passed. 8 plus 2, 10 plus 1. Oh, great. You're getting this. 3, my God, something at my level. I had this, I think. Are you sure? A. So instead of saying 101, 1011, blah, 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 again, wrong. Almost, almost, almost. Yes, you can also make these mistakes, and I'll fail with you the exam the same way that you do. Okay. Remember when I said don't do this ever in class live? So this is the reason, because you embarrass yourself without any end. Let's delete this, and let's have this on the blackboard. So, see, this would have been so much easier. That's why slides are good. Okay, the other way is just as simple. I'll try this again this time. Now I'm going to do it. C is, Zero, 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 1, 0. Oh my God, 1, 0, 0. 3, 0, 0, 1, 1. 0, 1, 0, 1. 0, 1, 0, 0. Then 8, 10, 11. Is it okay? What? Who says okay? Who says wrong? Let's see. This is okay, this is okay, this is okay, okay. Yes, I still have it. Okay. This horrible thing. Now, hexadecimal to decimal conversion. This one is not, I mean, you won't be using that as much, but it's the same way actually that you are approaching to it. When you have the first number, so the F that you see there is 16 to the power 0 plus 16 to the power 1 times A, and then 16 to the power 2 times 4. So now you know that F is 15, so it's 1 times 15 plus 16. Sorry, I cannot see it. So this is 15, sorry. 16 to the 0 is 1, plus 10, 4 plus, 256 times 4 is 1024, 16 times 10 is 160, 1 times 15 is 15. The result is 1199. My God, don't do this, Frank. Okay. Hexadecimal numbers are really, really useful when you are not dealing with 4 to 8 bits. Anytime you're dealing with a system where you have to express ones and zeros, that's 16, 32, 64, 128 bits, you will really appreciate being able to write things in hexadecimal. Now, there were also some other ways of expressing it. So 8 bits together is what we ended up calling a byte. It's a historical notation. And just like when we have our normal decimal numbers, we are identifying different digits. So we call this LSB, the least significant bit, meaning that if this was expressing your salary or your grade, this is the thing that matters most, least. And most significant bit is the one that makes the most difference. So this is why we call it the MSB. 8 bits is called a byte. Apparently, 4 bits was called a nibble. So I'm 53 years old. I've never heard it used in any technical discussion or in any documentation. Nibble. I just know that it exists because I teach this lecture. Might come in the exam, no. So once you are going further than 8 bits, as I said, you would be better off dealing with numbers written in hex format. Now, every digit is 4 bits, 8, 16, 32. So 32 bits makes 8 hex digits. And when you're looking at it, 2 of these together will represent a byte. So again, in a larger number, you're talking about the least significant byte, the byte that matters the least if it is representing a number, and the most significant byte, which represents the more important part of the number. I mean, if this was representing a value, you know, if this was your salary somehow. No. Oops, sorry. If you are getting If you are getting this as a salary, do you care more about this part or more about this part? Right? Who is hoping for more than this salary? Okay, wrong job. Okay. Now, there are some funny tricks and some funny coincidences. First of all, this is kind of nice. 2 to the 10, if you look at it, is 1024. Now, if in engineering speak, it's more or less 1,000, okay? It's not exactly, but you know, if you're talking about there is 1 kilo students here, right? Like 1,000-ish. And 2 to the 20, because you multiply 2 to the 10, right, is about 1 million. Well, it's 5% more than that. Or 2 to the 30 is 1 giga, is about 1 billion. It's 7% more than that. But, you know, you get the idea. This makes sometimes these calculations a little bit easier because you can use some funny shortcuts. Here is one number. 2 to the 34. Now, you can see this as 2 to the 4 times 2 to the 30, right? My math is really bad today, so I'm always asking. Does it make sense? Okay. So you know that 2 to the 30 is about 1 billion. 2 to the 4 is 16. There you go, 16 billion. I mean, you don't even, you know, you don't have to memorize it after a while. Some of these, more or less, you come into the right frame of mind. Now, in the meantime, people, these things will only be used by some computer architecture geeks and electrical engineers. In the meantime, these have become sort of kind of more mainstream, and that's why they started having SI standardized names. So when they say 2 to the 10, 1 kiwi, you mean really 1,000. When you say maybe you really mean this, 1 kiwi, you really mean this. So they have changed the things. So this is what I was talking about, estimating powers of 2. This is very simple now. 2 to the 24 is 16 million, so easy. We could also ask that in the exam. Okay. Any questions so far? No? Okay, good. Now I need to clean some blackboards. Conversion didn't work. Now let's see how I do with addition. Now, decimal addition, I hope most of us master this. I'm really bad at it. 4 plus 8 makes 12, so there's 1 carry. So then it is 1 plus 3 plus 6. That sort of makes 10. I have another carry. Then 1 plus 7 is 8. Then plus 1 is 9. There's no carry. Then I go over there. Now, when you do binary addition, things are actually the same. 1 plus 1 makes 2. Sorry. They're not going the way I want. Let's do this. Okay. I'll do it on this corner, sorry. Other way. So 1, 0, 1, 1, and 0, 0, 1, 1. Okay. 1 plus 1 makes 2. How do I write 2? So this is 0, this is 1, this is 2, this is 3, this is 4, this is 5. So 1 plus 1 makes 2. Right? So I write 0, and the carry comes here. Now I have 1 plus 1 plus 1. 3. Easy. Okay, I have 1. I put this. 1 plus 0 plus 0. You know, it's a challenge for me, these things. Okay. Hey, it was already there. Sorry. Okay. Now, there was a question. Remember, a few seconds ago, somebody was asking, hey, What about that 0 at the beginning? What is happening there? Now, I chose, or this is a number, let's say, carefully chosen. Look, this is still a number that we can express. What happens if I add these numbers? Now, I'm adding this number, and I'm adding this other number, which is slightly larger than this. Now, if you look at the left, and we do exactly the same thing, we get 1101. And if you look at it at the top, that's 9, that's 5. 9 plus 5 makes 14, hopefully. Is this? Yeah, right? But what about this? The number above? 11 plus 6 makes 17. No. I'm wondering if someone from ETH came in to check on me, saying there's someone who cannot do basic arithmetic giving lectures. So now, if you look at this, if I'm using an extra digit, this number is okay. But if I had only 4 digits, I would have had a problem. All of a sudden you realize, okay, as long as what you do add falls within the same range of the numbers, so the result stays within 4 bits, it's okay. The moment you go over, you will need either an extra digit or we might be doing something different. So digital systems, no matter what you do, will operate on a fixed number of bits. You speak of computers that have 32 bits, you speak of computers that have 64 bits. That means that they operate on numbers that have that range. As long as their calculation falls within the range that they are allowed to operate on, everything is okay. The moment you go out, you have a problem. So the previous example was 11 plus 6. If we were using a 4-bit computer, we would have had a problem. We may be aware of it, we may do something about it. If it's a computer, maybe there's a warning sign somewhere saying, warning, warning, you added these 2 numbers, but maybe that addition created an overflow. So that's an exception that we might have to handle. And this thing is very elementary. It's like your 3rd class, right? We are barely 2 hours and 20 minutes into this thing. Is it a problem? Oh, yes. So this is Ariane, the Ariane 5. They launched the rocket. And after a while, it exploded. Well, it veered off the course, and it had to be destroyed so that it doesn't cause anything. The problem was there were actually 2 stages, 2 different computers talking to each other, and this was working fine. One was, adding some numbers from a pressure sensor or something like that, and once it came into the more stronger Ariane 5 rocket while it was taking off, the numbers caused an overflow. He was reporting 16-bit numbers. The other guy was reporting different heights. It caused an overflow. The calculation went off. That completely destroyed the algorithm that was supposed to compensate for some changes. Result, 7 billion fireball. Okay? So as an engineer, you see, as a computer scientist as well, you see your first task is not to be involved in anything that crashes and burns and identified as a culprit. For this happened like 35 years ago. It's still in every class that talks about binary numbers. Now, the question is, given a number of digits, there is a certain range of numbers you can express. So what is this range, and what can we do about it? Now, we already discussed about it. I said n-digit decimal number, 0 to 10 to the n minus 1, n-bit binary number, 0 to 2n minus 1. So we already had these things. Now, we don't have any negative numbers. All of them start from 0. What shall I do with negative numbers? Okay, that is the first thing that everybody does. They say, you know what? Those are bits, right? One of the bits should not necessarily be the number. One of the bits should tell us if it's a positive number or not. You know, do you want 1 to be positive or 0 to be positive? Well, it's you came up with the idea. 0 should be positive. You know, back in the day, there are very famous mistakes made that way. Do you know what is the most annoying one, or do I know one? Do you know any such things which you could have picked randomly and the people chose the wrong one? Benjamin Franklin. Good old man of $100 bill fame. He, you know, he could have called positive charges and negative charges, and he just mixed them up. And so this is why, you know, electrons flow this way, but he thinks they flew this way. Still causes nightmares. Okay, so the first thing that people thought is exactly this. Let's use one sign bit and use the n-1 number, the remaining n-1 bits, as the magnitude. So, you know, we have this. And you know, this is also arbitrary. You know, they could have chosen to say the third bit will be the sign, but they were nice enough. They said the most significant bit should be the sign. Okay, so this is here. It tells you whether or not it's inverted or not, and the rest gives you some number. Sounds actually quite nice, right? Now, you know that when people talk about it at the very beginning of the lecture, there will be something wrong with it, right? Okay, just like in the movies, when you know there's a sequel, the hero cannot die, right? Okay, so we have a 4-bit sign magnitude representation of 6. So how does +6 how is +6 represented? How is -6 represented? So 3 bits, 1, 1, 0, that's 6. +6 is 0, 1, 1, 0, and -6 is 1, 1, 1, 1, 1, 0, my God. Now the range, not surprisingly, goes from -2 to the n-1, -1 to 2 to the n-1, -1. Tongue twisters. There are some problems with these numbers. Now, the first problem, which is actually the most annoying one. Remember how I was adding up these things? Now, if you try to add up the same way what I did before, you will realize that I will not get the number that I wanted. I cannot operate with the same algorithm that I was using. I cannot just add these numbers up and magically the result ends up being what it should be. So you can actually work out this example, and you see that, well, the number above is -6 and the number below is +6, but when you add them up, it is like 1, 0, 1, 0, 0. I should be 0, right? Sorry, is that clear? Did I go too fast? Help me out. Who says it's clear? Wow, great. Sorry. Sorry, I was boring you. The other problem is there are 2 representations of 0. This is -0, this is +0. It just comes as part of the deal because we are using one sign. And now if you're doing arithmetic, imagine that you are making a loop and you want to check if the number is equal to 0, you know, while larger than 0. You have 2 numbers to check for. It's really complicates things. So this introduces actually a lot of complexity in poor people who are designing hardware. And as a result, people said, let's do something else. Excited? No. So the one idea that they came up with was 1's complement. Actually, this is not the idea they came up with, okay? I'll be very honest with you. This is one of the lies that everybody tells. We are trying to bring you to a position where things will become smarter. 1's complement says, hey, from 0 to 127, for an 8-bit number, let's just keep the numbers as we know it. And then when we are going to negative numbers, let's just reverse them. So This is 127. If I reverse all the bits, this becomes 1, 0, 0, 0, 0, 0. That should be minus 127. And if I reverse this guy, the plus 0, well, this didn't work out, right? It should be minus 0. So one's complement is sort of okay. First of all, we are again going, if you're 8 bits, from minus 127 to plus 127. And if you're doing addition, remember that it wasn't working. There is a funny way of how to move around these things. So if you're adding 17 plus minus 8, and you do the calculation the normal way around, and then you get the carry that comes out, and then bring that guy in and add it up, magically, it works out to be correct. Now, this weird way of doing things is not so difficult to do in hardware. I mean, it's weird, I agree. But the people were trying to figure out what bothered them wasn't actually the range. And the two representations of 0 is quite annoying, but not being able to do the addition and subtraction the same way that you do addition subtraction for positive numbers was very annoying. So the ones complement gets rid of this problem. There is an obscure way of doing addition that things still work, but I still have the problem. I still have a plus 0 and a minus 0. So solution, and this is the genius solution, as much as these things can be genius, is to use 2's complement numbers. So it doesn't have the same problem as sign magnitude numbers. Addition works, and there's a single representation for 0. I'm going to show how it works. It has advantages over one's complement because we have a single 0 representation, which is great, and eliminates that stupid and around carry operation when you do that addition. Remember, I was showing you there is something funny. What it does is, he does this into the negative number calculation. So 2's complement numbers are generated by reversing the bits of the positive number and adding 1. Weird, but true. Okay, so this is 0, this is 1, 2, all the way to 127. Now, when you, let's take this 127 here, I will reverse all the bits and then add 1 to it. So 127 is the reverse of this, add 1. You can go to 1, the minus 1 will be by reversing this, so it will be 1, 1, 1, 1, 1, 1, 1, 0. And then I will add 1 to it. Ta-da! Who thinks this is weird? It is weird, okay? However, it works like a charm. So this is the beauty of it, and everybody uses this. There are some very good things about it, and the good thing for sign magnitude religious people saying sign magnitude is the only true way. It still holds true, actually, because if you look at it, all negative numbers have their most significant bit as 1. Okay? We don't have double 0. Stupidly, we have more negative numbers than positive numbers, but hey, the 0 had to go somewhere, so that's the price to pay. It's great. No? So the range is slightly funny, as you notice. It goes from minus 2 to the n minus 1 to 2 to the n minus 1 minus 1. So for 8 bits, it goes from minus 128 to 127. For, no, I'm not doing that. So if you want to take the 2's complement, if you want to negate a number, what are you doing? You invert the bits and add 1. Easy. So if I have this guy, 0, 0, 1, 1, what am I going to do? Well, I'm going to 0, 0, 1, 1. I'm going to invert the bits. So 1, 1, 0, 0. And I'm going to add 1 to it. So 1, 1, 0, 1. Oh, Frank. Invert the bits, add 1. Okay, so what happens if I'm trying to flip the sign of -8? So this is the same thing. Now this is a negative number. How do I know it's a negative number? Because the number has the most significant bit as a 1, and then some of it is, I mean, the rest, it's clear that it's a negative number. Why? Because I know that this number is being expressed as a 2's complement number. This is, I'll talk about that in a second. So I can invert the bits, and then I add 1, and now you see that this one ends up being 8. So this is 8, this is -8. This guy above is 3, this is -3. In 2's complement notation. Now, why was this interesting, or why do we even consider it? Because of this, the addition operation stays exactly the same. So you have +6 plus -6 in 2's complement notation. We are trying to add them up, and you will see that if you are able to ignore the carry, this part is 0. So the upper part is 6, the lower part is -6. You add them together, you get this. Now, this is -2, and this is +3. You add them together, the result is 1, just like you expected. However, the adder doesn't have to know whether or not these numbers are positive integers or are 2's complement numbers that can also represent positive and negative numbers. The only thing, there was a question at the beginning where I said it's very good, is we have to agree how the number is represented and how many bits are used to represent it. So this is one of the interesting parts of these things. It's me, it's us, that decides how the number is being encoded. Once we decide on the encoding, computations can be made with that encoding. And as long as we are within those ranges, the results will be like we expect. But any given number, like if you see this, 1, 1, 1, 0, now is this, what is it, 14? Is this 14 or is this -2? What do you say? It isn't clear, right? You have to know whether or not this number, the thing that you see here, is this sequence of bits expressed as a positive integer, or is that expressed as a 2's complement number? Somebody's scratching there. No questions so far? Yes?
Is the algorithm used in processors?
All processors rely on this. All process, because you know what? Making the addition and subtraction is so much easier if you have this number format. You use exactly the same hardware, because you see, it doesn't matter if you interpret this number as only a positive integer or a 2's complement number, you're doing the same thing. The processor, if you want, doesn't have to know how the number is interpreted. He will do the right thing. So that's why it's great. My God. How many? What's the time? Oh, 2 minutes. We'll manage it. Okay. So at any time when you're doing these calculations, you may start a calculation saying that, 6 bits should be enough for my calculation. And now you realize, oh my God, I mean, I'm adding all these numbers. It may not be enough. I may need 16 numbers. Or, you have 32 bits, you want to go to 64 bits, whatever. It is possible to extend it. Now you have 2 options. Because the number you use, you have to know, am I using 2's complement numbers? Or am I using only integers, starting from 0, only positive numbers? So we have 2 options. We either do a sign extension, meaning that if the number gets larger, we copy the most significant bit and say, hey, if that's 1, I'm just going to expand it by 1, or we make a 0 extension. So that depends on how the number is interpreted. Now, this is a 4-bit representation of 3. And, you know, I want to make it an 8-bit sign extended value. Well, I'm just adding zeros if I'm doing, I say this was its sign, it was 0. So I'm just extending it. I just copy whatever this is as many times as possible. Now, if this was -5, so this is -5, hopefully, and you take this and you want to extend it to 8 bits, well, the sign was 1, so we are copying it over. If you do the conversion, you will realize that this will still be in 8 bits -5. If you copy zeros to it, all of a sudden, you have a much different number, because if you start putting zeros in front of it, the number that was -5 turns out to be 11, right? Okay. Whew. Now, the other option is not thinking about what this is and just putting zeros in front of it. You can do that only if you are dealing with positive numbers, because if the number was negative, like this one is -5, if you are adding zeros in front of it, all of a sudden you have a completely different number. So here is a little comparison between the different number formats we are using. If you have unsigned, the range goes from 0 to 2 and -1. So this is, if you are looking here, this is a 0. Unsigned, I can represent 16 numbers, and I start from 0, go all the way to 15. If I have signed magnitude, well, if I have signed magnitude, I'm here. 0, I have 2 versions of 0, and I go from -7 until 7. Now I'm losing this one number that makes my life difficult, first of all. And second, computation is a bit more complicated. So the 2's complement this time goes from -8 to +7, which is good. I'm not wasting 2 zeros. 0 is just this guy. And I can still use the same adder that I use here. I just have to be careful when I am extending the signs. So this concludes this part of the lecture. We are just trying to talk about integers. Floating point numbers will come at a later stage when we are talking about that. We want to express decimal numbers using only 1s and 0s, how to simplify writing binary numbers in hexadecimal, adding binary numbers, and we wanted to, I mean, all this story is to show you why we use 2's complement numbers. I hope I was able to convince you that it is useful. You still didn't see it, but you're like, there is some reinforcement, right? Frank says it's useful. And once you, in the exercises, you'll actually see this in action. This is to bring you to the point to explain why 2's complement numbers make sense. I think there should have been a break, right? Let's have a break. Let's continue at 1:15. Okay, okay. 1 more hour. One tiny more hour and then we are done. Okay. So since I'm from electrical engineering, I want to talk a little bit about electrical engineering. I'll just talk about annoying things, current, voltage, capacitance. Then we will talk about what is a transistor, why do we care? We care because we want to build logic gates, and logic gates is what will make our computer work. So this is why we care. I'm not going to bore you too much, and then there's going to be the Moore's law, which is fun topic. And if you have any time left, who thinks we'll have time left? Oh, okay. Some people still believe in fairies. Okay. So, remember I showed you this? Remember I told you I'm lying about it? So this course is about architecture and we will never look here. So this is the only lecture where we will slightly look here. Not too much, but just to show you what is going on. So I'm from electrical engineering. This is why I have to say a few words about it. What do these guys do? And what is these electrical engineers? Why should you care about them? Not much. So these things are horrible pictures for me because if I were to take my job seriously, I had to make them every year because there's a new iPhone. I don't even remember which one this is. This is the iPhone 5. What do you have currently? 14, 15, something. Okay. The good news about older electronics is they are more visible. What happens over the years is we integrate more and more. This will tie into the Moore's law. So when you open something like this, you see that this is actually the heart of it. So this is the application processor, meaning this is where the programs run. This is the heart of the system. However, there is a bunch of other stuff. There is a modem, a modulator, demodulator, which is used for communication. There is a number of power amplifiers. The power amplifiers help to drive a signal to the outside. There is the antenna chip system that goes there. There is some memories. There is another Wi-Fi module. There is some sensors in it, other sensors, touchscreen controller, and a number of things. So if you go into any kind of complex electronic system these days, which today also would include your refrigerator or things like that, there is a power subsystem, processor, memory, antennas, telecommunication. Your fridge has to wirelessly transmit what the yogurt looks like, audio subsystem, camera display driver, external things, etc., etc. Now, in electrical engineering, it's not like everybody does everything. There's a lot of different specializations. So one group of people are actually dealing with the problem of transmitting and receiving signals over the air. So this is, they use electromagnetic waves, their properties, to form, transmit, receive signals over the air. Now, when you do this, unfortunately, there are some evil things that are called noise that creates problems while you're trying to receive the signal. So there are clever ways of encoding your system so that even there is a lot of noise, you can still recover what is going on. This entire thing is communication theory, and you find efficient ways to encode data so that the communication channels are, you can send more data over them. There is the audio-video signal processing, how to manipulate signals that you capture from your microphone, from your camera. There are analog electronics. Analog signals are continuous signals. They measure physical quantities like sound, like temperature, and you need to sometimes convert them to the digital domain for further processing, or you want to reproduce the analog signal from a sequence of digital values, meaning that you have your MP3 player. Does anybody know an MP3 player? Oh, okay. You still use them, or this is like childhood memories? Okay. Walkman. Seriously, you had a Walkman? You had a Walkman. Great. Retro. So, digital electronics is the topic of this lecture. These are the people that deal only with ones and zeros. So this is a very brief overview of what they do. Now, when you have a circuit, and this is, we need to remember this, when you have a circuit design or anything, you need to optimize a number of things. The first thing is area. You can realize the first the function using maybe different number of gates, transistors, different size, but you pay for the cost of the manufacturing. The more devices, the more transistors you need to realize your function, the more you will pay. So you have an interest in reducing the area because it will cost you less. In other words, into the same area, you can put more functionality. Now, speed and throughput. Who has been to MediaMarkt or Interdiscount? So the dude that is selling you your cell phone, your laptop, what did he say? How do they sell it? There's like this 2 gigahertz thing, and there's a 2.4 gigahertz. Like everybody agrees that 2.4 is better than 2, right? No? You didn't? Okay. Some people do. Speed, so that can be the operation speed of a device, or sometimes we talk about throughput. It's similar when you talk about your cable-com network connection, whatever, 500 megabits per second or 1,500 megabits per second. One of them seems to be better. Power and energy these days is quite interesting. People make a lot of deal about the power that we use, you know, renewables. On the other hand, energy is also something that people care about a lot. They are related. They are very related, but they are different. Energy is, for example, the content of your battery. How long can your laptop operate has to do more with the problem of energy. Whereas when you have a device that draws, that, for example, collects energy from a solar cell, you get a certain amount of power at any given time, and you care about the power consumption of the device so that you can sustain the operation. So high-performance devices the same way. When you have a data center, the power, when you say this processor consumes 100 watt, what happens to the 100 watt? You know? Yeah? It's converted to heat. It heats the room. And if you think about it, a processor routinely consumes 100 watts, but it's about 2 centimeters by 2 centimeters. That's more than your cooking plate. That's actually close to a nuclear reactor. The fuel rods have a similar thermal density. If it heats any more, the guy will melt. Actually, a computer without cooling will melt instantly, like within a second. So high-performance devices also have an issue to keep the power within the thermal limits so that it doesn't destroy. Now, this is talked about a lot. One thing you also shouldn't forget is you also want to optimize the time to design the circuit. So the designer time, how much effort is needed, is also a big part of the equation. You don't want to spend years and years making the perfect device. You want to sell this thing as soon as you can because someone else will do. Now, the requirements also depend on application. So something that is, you know, a hearing aid probably cares more about different things than something that goes to space or something that's forgotten on a beach or a high-performance computing infrastructure. Meaning that depending on what type of thing you are doing, you will care about these things in a different manner. For space, for example, what do you think is more important for space? Yeah? Reliability. One thing else? That's very good. Yeah? Okay. Yeah. Yeah? Weight. You have to, you know, this guy is doing this because he's trying to bring, I don't know, 3 tons of thing to the orbit. And if you say, this requires a car battery like that of Tesla, it will have to be much, have to do 2 of them, right? Okay, so these are my principles for engineering. First number, good engineers are lazy. We don't want to work unnecessarily. So we want to be creative. Instead of doing the same repetitive function over and over again, we want to be the cool dudes that are doing something else, but not the same repetitive things. They know how to ask the question, why? Why am I doing this? If something is repetitive and looks like it's stupid, I mean, you know, I'm not saying rebel and, you know, go out to the street and destroy things, but, you know, just ask the question why and get an answer so that you know why it is doing. Engineering is not religion. I know that all engineers are deeply religious. I don't know, Python versus Rust. Who's a Rust fan here? They will be very loud. Is Rust a good language? Yeah, see. It's fun, you know, there's nothing wrong with it, but when you are making your decisions, know when to switch and don't stay, I love Rust and Rust will do everything. There is a lot of things where Rust is great, I'm sure, and there is some things where probably we should not be using it as much. I don't know. Don't look. They are looking at me like that. Okay, and keep it simple and stupid. Our life is about managing complexity. Let's not add more to it. We want to make things simple as much as possible. Now, electrical engineering things or physics that you have to know for all digital electronics is actually Uri, Swiss people? Who's from Uri? Canton Uri, yes, there you go. Okay, V equals I times R, so if there's a potential, current will flow over a resistor, and the current that flows through the resistor will be proportional to the resistor, and their thing will be equal. Then the second thing is the time it takes for a voltage to charge a capacitor. If you look at it actually in time, so you have the previous circuit. I mean, this is from physics lessons. I'm not asking this in the exam. It's just, it is useful. So this RC creates a time constant, and you know that this guy will take, you know, at the beginning, there is no charge on the capacitor, and then it charges and charges and reaches the max charge after a long time. At the RC point, it already reaches 0.69, etc., etc. The point is, that capacitor takes some time to charge, and that charge depends on the time constant, which is given by the resistor and capacitor. These are physics lectures to keep it. Now, this will become one of the main problems when you are making digital circuits. Why something works at 2 gigahertz and not at 3 gigahertz is there will be capacitors to charge, and those capacitors can only be charged with a limited current. And because it takes time to charge them, we won't be able to do this charging process fast enough. How can I reduce it? Well, increase the current, reduce resistance, reduce the capacitance. You can do it faster. So this is what's going on. That's in a nutshell. Obviously, if you're in electrical engineering, we teach this to you in a semester. Good for you. Now, let's go and build some microchips, because we know now everything about it. To build microchips, you need conductors that conduct electricity. Here's an exam question. What's the best conductor you could find? Back in, yes? Silver. So good. Silver is the best, yes? No, horrible conductor. Silver is the best one. I mean, he's right. He's really right, yes. Gold is a decent conductor, is not as good as silver, but gold, you know what's really great about gold? It doesn't rust. That's why gold is used everywhere. Gold is like this thing that, you know, nothing happens to it. Silver, on the other hand, if your family has some silverware, you're polishing it, it will, I mean, it's a reactive material like crazy. And don't ever bring into manufacturing discussions, why don't we use silver? People will kick you out. Now, if you have conductors, you mean that you conduct electricity. And if you have two conductors, you have to make sure that they don't touch, otherwise you cannot keep them separate. So you need some insulators. And one of the best insulators to be used is glass, which is silicon dioxide, which is a very common and very nice thing. The other one, which is a very good insulator, is air. There is all kinds of other things, most plastics, wood and other things are also insulators. But for manufacturing purposes, the silicon dioxide is a godsend. And then we have these semiconductors. Who has heard semiconductors? Great. Semiconductors are great things. Do you know why? Yeah. Sorry? They do both. Yeah. Actually, let's take a look at a semiconductor. So silicon is a semiconductor. It forms a perfect crystal structure. I'm lying here because it's not straight. It will be a three-dimensional structure, but it's so much easier to draw it this way. Now, when you look at it, the outer valence band has 8 places for 8 electrons, and 4 of it are occupied. So it can form nice and strong covalent bonds with all its neighbors. So once it does so, every silicon atom in this crystal structure is super happy. This guy is actually not a very good conductor. It's actually a, can I say this? Can you? No, it's not, it's a poo-poo conductor, okay? I hate this YouTube thing. Okay, it's a poo-poo conductor. So why do we use it? Why is it so interesting about it? Well, it's not a good insulator because there's still like things can move around. I mean, it's also not like it doesn't conduct. It conducts a little bit because, you know, give it some energy, these guys will move, that movement will break some things, and some electrons will go back and forth. It's not like it doesn't conduct. It conducts, it's not a very good conductor, it's not a very good insulator, it's a semiconductor, not a good one. Why do we care? We care about it for one simple reason. If we have this nice structure, we can manipulate regions of it according to what we want. That makes it interesting. So we can take out this one silicon atom and replace it with a phosphor atom. We take this nice covalent bond silicon atom and say, go take a hike. This is my cousin, phosphor. He comes in here, and that guy has an extra electron. And all of a sudden, this region is negatively charged. It has an electrical, its electrical property has changed. It was completely neutral, blank, boring. Now it has become N-type region. You can do the opposite. You can take one region and say, I am going to replace it, in this case, by a boron atom, and that atom has one missing electron, which means that this guy is hungry for an electron. Any electron that flies around will say, ah, here, boom. So it attracts, it's positively charged because it's missing electrons. Now will come the question, how do you manufacture these things? What's so great about it? Well, you take a pure silicon thing, and I'm not joking about this. This is exactly what they do. So there's a semiconductor. You take some boron atoms, not in your hand, and then you look at the silicon structure and you throw it. If you have enough energy, you will displace that atom, and the boron atom will get stuck into this lattice. Of course, there will be all kinds of drama, burning things, families broken up, crying, and things like that. And then there will be an annealing session where you heat this thing up a little bit and allow the crystal structure to reconvene. This is how we make these things. And semiconductors are great because you can engineer its properties. You can make P-type and N-type regions on the same surface. So you can control, you can engineer, you can play around with it. So you start with a pure semiconductor and you can combine P and N regions next to each other. And as you get better and better at displacing atoms and putting them in place, you can make these structures smaller and smaller. Now, out of these structures, you can make interesting electrical devices, which we will not go into details. Normally, there would be a semiconductor device lecture where you talk about diodes, and then transistors, tristors, etc., etc. How does it sound so far? Okay, so let's go to the transistors. Now, notice that I told you I can engineer these things. So we can take a silicon surface, make sure that the bottom part is more p-doped. Remember, I can do it, right? I mean, give me a little bit of time. You know, I'm there throwing chalks at the board and things like that. And then I engineer some shallower N regions. Never mind why I do this. Let's just look at the result. So I will connect a resistor and connect it to some power supply, 1 volt, 5 volt, whatever. And I'll connect the rest of it, this part of it, to ground. Why am I doing it? Well, I'll get to it, right? So this looks like this. There is a positive voltage here, there is 0 voltage here, and in between there is no connection. Now, by engineering a little bit more, we are adding what we call a gate, and that gate controls the access between these 2 points. How does he do that? Well, we are applying a gate voltage here, and depending on the polarity of this voltage, we can open a little channel here between those two, allowing current to flow this way. So I can create out of this very innocent looking tiny structure where I have, let's say, a P base, P-doped semiconductor base. I form some N regions and I put a gate on top of it. By controlling the voltage on this gate, I can create a switch. Just like the old electric switches, which unfortunately there are no more. Like, oh yeah, there's one. Something like, you know, those really old switches. Does it seem like interesting? It shouldn't be, because it's, I mean, this electrical engineering stuff. But once I have this one switch, and this is a transistor, remember, yesterday I was talking about that the M2 has 20 billion of those in 1.3 centimeters, right? 1.3 centimeters by 1.3 centimeters, 20 billion of those. One of them doesn't do anything special. With 2 of them, I'll just go a little bit forward. Forget about the details. With 1 of them, I can make 1 switch. Combine 2 of them and put them together, I have a structure like this. In this case, if I have here what we call an NMOS transistor, if I open this and close this, this guy, the output will be connected to the top. See, this guy is closed, this guy is open. So this output, this part, is actually connected to the higher voltage. If I go the next way around and flip them, now this guy is closed, this guy is open, and the output went down. Okay. If I used a high voltage to bring this down, I have actually inverted the function that I had at the beginning. It's a very, very silly and simple function. But in a few minutes, hopefully, I will show you that we can do more with this. And once we start doing a few things, you realize that we can build more and more stuff. Now, I'll have to go back a few slides. I was thinking a lot about them because people got confused by it a lot. Remember that I was putting here this resistor. It's not so important why it's there. It acts as a load. And at the beginning, 1970s, the only way we were doing circuits were these. We were putting these resistors. Resistors resist. Resisting cost, heat, power, losses of current. So people were upset. We were only doing NMOS transistors that were only switching when you had a positive voltage here. Then we were able to make PMOS transistors that were just the dual. They were switching when this voltage was low, but we could do either one. The big breakthrough came in 1973, 75, where they were able to where they were able to join both of them together. So you have both the NMOS and the PMOS together. They call them complementary MOS, CMOS. And that changed everything. You know, the good news is, when this guy is working, this guy is the load, and when this guy is working, this guy is the load, but they do not consume active current. There is no, they don't burn any static power. So this was great. This is what actually started the entire thing. The input is not resistive. There is no current flowing through. The input is capacitive. Remember the one that I was showing? There's a simple capacitor. You charge it. Once it is charged, once the capacitor has reached its value, it has reached its value, so it has flipped. And when the output is stable, when the output has switched from 0 to 1, there is no additional current flowing. The electrical properties, if you want to draw them, make them, manufacture them, are determined directly by geometry. This is like the greatest thing ever. You have a small transistor, you don't like it, make it twice as large. If you make it twice as large, it will be able to drive twice as much current. How great is that? And all of them wouldn't matter at all. It is also incredibly simple to manufacture. Number of steps required to make CMOS transistors have been very easy to optimize, and this is why they have survived for more than 60 years now. They are the mainstream. There were many, many attempts to say, hey, I could do different types of things. I could use different materials to make transistors. It is correct. There's many, many different ways of making transistors. It's just that, especially for digital circuits, these guys are so simple, so fast, so reliable. People are using them over and over again. Now, I'm going back to the slides from the lecture, from the textbook. This is the simplest logic function we can build. I have an input, call it A. If it is binary 0, the output is 1. If it is, the input is 1, the output is 0. So we're just inverting the signal. Boring as hell. How can I do this? I have one NMOS and one PMOS. So if A is 0, well, I was too fast, baby, but hopefully you will remember that when 0, the PMOS is on when it is 0, and the NMOS is on when it is 1. So when A is 0, the input is 0, the PMOS is on, the NMOS is off, meaning that the output is connected to VDD, the output goes high. When the input is 1, so this guy is 1, the NMOS is switched on, meaning that the output is connected to the ground, and the output is 0. I'll say a lot of 1 and 0. Is this sort of okay? 2 switches? Sort of. Say okay. Okay, let's make a few more, and then let me ask it again. Now, we can do it a little bit more complicated. If I 2 guys in series here, N1 and N2, when will the output be 0? Well, the output will be 0 when both N1 and N2 are on. Every time off, it will be something on. So we can, my God, let's pick this guy. When A is 1, B is 1, both PMOSes are off. The ones at the top are off. N1 is on, N2 is on. This means that the output is connected here to the ground. In all other cases, it will be one of the PMOSes or both of them pulling this thing up. Now, the way these things are constructed has a general style. And the general style works like this. I have a number of inputs. Those inputs go both to an NMOS and the PMOS network. At any given time, only one of this structure works. The other part doesn't resist. Does it make sense? So the output is either pulled down by NMOS or pulled up by PMOS. At no point do they fight against each other. How do I manage this? I construct it in a dual fashion. So whatever function is here is mirrored. Whatever is in series is in parallel. Whatever is in parallel is in series. I mirror the function, and I use the opposite transistors. So here I use NMOS transistors. There I use PMOS transistors. NMOS transistors switch on when the input is 1. PMOS transistors switch on when the input is 0. Yeah. Let me see. Does it sort of make? Yeah. Yeah. Yes. Excellent, excellent question. Yeah, I'll do it. This part, I'll do it also there, okay? So, an NMOS is a switch that is controlled by this gate voltage. And this NMOS switches closes when the input is 1. So it allows current to flow through. Okay? So this is the NMOS. To be fair, let's go to this part. Oh my God. Go away. Ugh. No. Here. No. Oh my God. Okay. A PMOS, the PMOS has like this little rounded thing, is very similar, is also a switch, but the switch closes when the input is 0. So when it is 0, it closes and it allows current to flow through. So you can say, when this is 0, this guy is turned on. And when this is 1, this guy is turned on, and this guy is switched on. Does it make sense? Now, the funny part is, when you are putting together a function, you can take your output, so this is your output, and you can put your function here. And you say, let me make something more complex, right? So I have an NMOS. Something like this, A, B, C. 3 inputs. And when does this Y go down? Well, it goes down when A and B are 1. A and B are 1. Or C is 1. It goes down, so it's negated. We will come back to this in a couple of minutes, okay? Or actually next part. And the PMOS part, so this is the NMOS part, the PMOS part just reverses whatever is in series is made in parallel. So this is the A, this is the B, and whatever is in parallel is in series. So this becomes like this. Finished. I know I'm showing off, that's not nice. But just to show you the principle, once you know what function you want to make, it's not that you memorize what I did here. What I wanted to say is, the logic function you realize here, and this part pulls the network down when when your logic function is realized, and this network pulls the output up when they are done. The trick is to construct it in a way that they don't work against each other. And this is not our job, okay? We are not trying to learn how to do this. There is a bit of explanation. We are not asking in the exams how to do this. If you're really, really, really interested, VLSI 3 at DA TED takes this to the max. I don't see people running out to go there. Okay, so what's the time? Oh, perfection. I only have 20 slides in 10 minutes, no problem. So logic gates are here to perform logic functions. They can be extremely simple things, like inversion, and, or, NAND, NOR. They can be single input. There are not many single input functions, right? So one input, you could either invert it or keep it the same. 2 inputs, 2 input AND, 2 input OR, XOR, NAND, something, and then we can have as many input gates as possible. So here are the simple gates. The NOT gate, we already looked at it. A0, 1, Y is just the opposite. It's also called an inverter. And the buffer, that seems like a complete waste of time, right? The input is 0, the output is 0. The input is 1, the output is 1. Why do I even care? Seems really useless. There are uses to it. It will become hopefully obvious, not obvious, but we will understand it better in a couple of lectures. We use this thing to strengthen the signal, to repeat it, to act as a buffer. That's also why we call it a buffer. Now, notice that this inversion, the logic inversion, we usually ends up with a circle at the output. Now, we also have two input logic gates. These should be familiar to you. I have two inputs, A and B, and the output will be A and B, 0, 0, and only when both of them are 1, we have an output. Or we have the OR gate. These are things that we know, hopefully. AND gates, OR gates, anyone never heard of them? Never? Never heard of AND OR gates? Okay. Not that complicated. And if you look it up, actually, 1 and 2 input logic gates, there are not so many of them. So these are buffers and inverters. We saw the AND gate, OR gate. There is also an exclusive OR gate, which means that the output is only 1 if only one input is 1. If both of them are 1, they are 0. And then they are the ones with inverted output. So this is the AND gate. If you invert the output, you have the NAND gate. If you have the OR gate, invert the output, we have the NOR gate. You have the XOR gate, you invert the outputs, we have the XNOR gate. Now, we could stop the lecture right now. Don't go. I said we could. We will talk about it next week, but there is the entire, let's say, Boolean algebra. And you can prove that if you have this gate or this gate, you can do any function in the world, any digital function. Those two are enough. So if you know how to design this, that's it, we are done. Not entirely true, we can do it, but it's not necessarily the most area efficient one, not the fastest one, not the power energy one, and maybe not the design time one, but functionality-wise, only knowing how to design this gate is enough to do any kind of logic function, which is kind of nice. Now, there are also multiple input logic gates. You can have 3, 4 input gates, 5 input gates, whatever. We can have compound gates, you know, and into or into and, those inverted. We have other cells. My favorite are multiplexers. I'm in deep love with, I have a love affair with multiplexers. There's adders, will be part of the exercises. And this more or less sums up the type of things we can do. Notice that we didn't talk about what they are good for. But we just realized that if I have like these basic binary things, I can represent some numbers. I have these gates that seem to manipulate them in some way. I can AND them, I can OR them, I can invert them. So some things can be done. And we see that somehow transistors are related to it. Now, I was telling you about the logic levels. We agreed at some point yesterday, we said, you know, we need 2 discrete voltages to represent 1 and 0. However, we don't seem to care so much what it is, right? It could be 1 volt, 5 volts, minus 7 volts to minus 3,514 volts, whatever. We could pick different things. So in our life, to make life easier, there have been some standards over the years where chip manufacturers have realized and came down to certain voltage levels. We started with 5 volts at some point, and then we went down 3.3, 2.5, 1.8, 1.5, 1.2. These days, it's even 1 volt or 0.8 volts are used inside the chips. We will not go too much into details, but the voltage levels have dropped. Now, the problem is, once you have a voltage level, once you say it's 5 volts, how much 5 volt is 5 volt, right? What you use is actually a range of voltages that represent that value. So it's not exactly 5.0000. So if it's 4.99, so you still call that the range. So I'll just come to this thing. What happens is, for the driver, you say for the output, any range between this upper level and the lower level is considered to be high. Any range between here is considered to be low. Anything in between is considered to be, oh my God, what's going on here? At the input, so once you have your signal, it is going over a distance. And while it goes over a distance, it may get disturbed by noise, by other factors. So you allow a little bit of noise margin. So if this is 0.5 volt, you say, hey, some noise can come, but if it's below 1 volt, I'm still going to count it as 0. The same way for the high, here maybe you wanted 5 volts, so you said 4 volts is also okay, but then when it travels to your next circuit, you say, you know what, 3.5, I'll also take it. But if it falls into this region, you say, nah, that's not good. Now this part, these noise margins, is the main reason why digital circuits are great. Because the signal quality can be restored as long as you stay out of the forbidden zone. The output 0 doesn't have to be a perfect 0. It should look 0-ish. And the 1 should look 1-ish. And as long as you can still distinguish it, the receiver can reproduce the signal without any loss. The reason why digital recordings are so much better than analog recordings is you are not trying to capture the phase, the amplitude of a signal perfectly. You are able to, just keep the 1s and 0s that correspond to the signal. And as long as you can keep those noise margins intact, you are good. So this is the main reason we do this. Let's see. 3 minutes for Moore's law. Great. Do you know Gordon Moore? Personally? Gordon Moore was founder of Intel, one of them. And so he's sitting in a meeting because he's a famous and rich guy. They are talking and he's doodling. And this is actually what he ended up doodling. This is from his first publication. It's quite early, right? He's actually only here, so we are in 1965. So what he's plotting is the number of components that they can manufacture. And he sees 1959, we made 1, and 1962, we made 3, and then we made this, and then he's saying, you know what, I think this will go on this line if we continue doing this. What he actually says is slightly more complicated because as you try to put more and more devices, at some point, see, you're trying to put number of components onto the device, and up to here, it sort of kind of pays off. After that, you have problems with manufacturing yield, meaning that you cannot make them so well again. So this curve starts going up. So what he's trying to follow is the bottom of this curve, which is a slightly more technical thing. But Moore's law is not a law, okay? You won't get arrested for breaking Moore's law. Very important. It's what we call a self-fulfilling prophecy. It started as an observation. It's relatively vague and it's catchy. You say you can double the number of transistors per chip area every 2 years, 18 months, depends on how you interpret it. It's not terribly accurate, but it gives the industry a very good direction to follow. And it's also very easy to cheat. People cheat with numbers all the time. So cheating with Moore's law is no exception. Now, this is a great guy, Carl Rupp. He in GitHub, he has this microprocessor trend data. He collects like thousands and thousands of things, and he plots them for different things. So the transistors is yellow line, and so this is logarithmic on one scale, and these are the years. And you see that the number of transistors keep on increasing. So 10 to the 7, right? So that is 10 million, the top is 100 million. Now we have this in billions. And essentially, this is what Moore's law was predicting. Now, you might be arguing about the curve and things, but you see that a ton of things are happening. At the same time, he's also putting different things. like single thread performance, the frequency, the typical power, number of logical cores. And you see funny things happening because at the beginning, the number of transistors helped us become better. And after a while, we hit what we call a power wall. You see this? This is 100 watts. After 100 watts, things started melting. So we couldn't go any faster. The frequency was the same. It went all the way to 2005. If you were in those days, there was the megahertz wars. Intel was bringing out a processor that was 5 megahertz faster than the other one, and he was battling back. And they were trying to make 10 gigahertz, 20 gigahertz, 30 gigahertz processors. For things that will become clearer later in the lecture, this didn't work, so they stopped. What happened? Well, I have more transistors. What do I do with more transistors? They said, let's build more cores. So this is how it went. And as a computer scientist, you will appreciate one of the problems then becomes, how do I make use of that much parallelization? How can I have parallel programming things that we can keep? Now, I see that I'm out of time. Don't worry. I want to power consumption. Let me just wrap this up. How do we keep Moore's law? Well, we end up being better at manufacturing. Remember me throwing that chalk? We are getting better at throwing that chalk. We develop materials with better properties. You know, silicon dioxide is good, but maybe hafnium dioxide is even better. Making sure that all materials that we use are becoming a challenge. If you go a device circuit, a device systems seminar or things like that, you can play a periodic table bingo every time you have a new thing and you cross off a line. We optimize the manufacturing steps. You are manufacturing things that are 7 nanometer wide using light. How does that even work? And we develop new technologies. I'm going to skip the power consumption and let's just wrap this up. What did we learn? What a transistor is? We know at least the least amount of thing that you should understand is that these transistors act as switches. Switches combined in a smart way can build logic gates, and those gates end up helping us to build larger and larger systems. Power consumption we didn't talk about. I'll try to cover it in another lecture. What we will do next week is, now that we know those logic gates and things and ones and zeros, we need to develop a theory of how we can map our problems into those gates, into those ones and zeros, and make sensible things out of it. Next week will be terrible, okay? It will be boring. Please hang through, come here. We'll try to explain it. I'll make less mistakes if that's possible. And see you next week. Thank you.